Back, ladies and gentlemen. We're going to be continuing our discussion about the physical properties of matter today. We're going to be moving on to the kinetic molecular theory, and we're going to do things a little bit different because the first step is to watch this cool animation. What we're seeing here, of course, is diffusion in action, and this is only possible because of the kinetic molecular theory. What is the kinetic molecular theory, you might ask? Well, we can try breaking down the words. Theory means it's an idea that explains why something is the way it is. So in this case, why diffusion can happen. Molecular means that we're talking about individual particles. Theory, well, we already did theory. Kinetic is the Greek word for motion. So this is the theory of particles moving. I told you guys before, and I'll say it again. Scientists like to make themselves sound smarter by using other languages, but basically describing exactly what it is. Now, usually I would get you guys to read up on page 385 of your textbook and fill out the next several pages of your booklet to explore and expand on what we see there. I'm not going to ask you to do that this time, or at least I'm going to ask you to do it. I'm going to pause for a few seconds, and then I'm going to continue with explaining everything that you need to know about this. But either way, feel free to do some reading. I will make sure to post these textbook pages online in short order. But there we go. That was my pause. I took a drink. Kinetic molecular theory. What do we see with this? The kinetic molecular theory was designed to describe gases, and it makes three assumptions about how gases work. Assumption number one, all particles are small hard spheres with no volume. So basically, gases are made up of a bunch of tiny marbles. That's what we're basically saying. Okay? Assumption number two, particles move constantly but randomly. So you can't really control what they're going to do. Now, if you take a look here, right, back at the little animation, it's basically what we're seeing here, right? The particles are moving around at random, and they are tiny, hard spheres. So there's only one other thing left on the list because there's only three different rules. 3, particles bounce rather than stick. If we put that in less simplistic language, the official dialogue, the official words for this would be that particles have elastic collisions, which is the fancy way to say that they bounce and don't stick together in any way. That's kind of it. That explains how gases behave. Why is this important? Well, the idea that gases, well, let's not get to this yet. The idea that gases are these small hard spheres that bounce against each other at random and then don't stick together is the reason why diffusion happens. The smell that starts in that corner of the room, as we've mentioned before, it starts to expand outward. It bounces and clicks against the others, and they all jostle around, and then they slowly spread out. That is literally what we are seeing here. The diffusion of the gas out of the bottle is being helped by these other air particles, bouncing them around, right? You can watch individual particles. There's one here, and it's going to come up here like this, and it gets bounced, and then it gets bounced down to here. It goes up like this. Other particles take other paths. There's no specific way that things have to go. It's completely random. But this is why this happens, because they are tiny spheres, because they move randomly, and they don't stick together. Now, this theory was developed for gases, but we also apply it to solids and liquids, but the rules don't really work. I mean, think about a liquid, right? They do have particles, so they do have those tiny spheres that take no volume. And they do move randomly, but they are sticky because the liquid clumps together, right? That's literally what's happened here. That's why the liquid's in the bottom of the glass, because it all sticks together. It still moves randomly. Individual particles are sloshing around like crazy, but the random motion is constrained because the particles are sticky. Solids, on the other hand, have particles, but they don't really move very much, and they stay very close together. Very close together. They do move, technically. They vibrate. They hum in place. It's kind of like when you're stuck in class, and the teacher's been talking for a very long time, and you really want to get outside, you really want to go to gym, or to just have the day end, and you're sort of sitting in your chair, and you're fidgeting, you're moving around, you're stretching out. All of these things are what the particles do in a solid. They want to move, but they can't. And much like with a student sitting in class, how much they want to move, how much they can move, will vary. It will change and adjust over time. It depends on how antsy the student is, how much energy the particle has. If the student is feeling very calm, then they won't move very much. Probably not at all. They'll just like stare at you. If they're feeling particularly energetic, they'll be all like, I don't want to be here. Same thing with the particles. In solids, some particles will stay very rigid and some particles will move around a lot, and it depends on how much energy they have. But we're going to talk about that more in a second. First, let's summarize all of this. What we see here, right, is that all of the particles are small, hard spheres with no volume. Some of them, 2 of them, move constantly but randomly, and only really the gases bounce rather than stick. The other 2 are very sticky. It's kind of why they exist as liquids and solids in the first place. Now, I mentioned that the solids will still move, right? They do still move, so it's like they're like partially ticking this box, but they don't move much. This comes into sort of the relationship between energy and temperature. We've talked about energy and temperature a couple times, right? Like last time I ended up talking about plasmas and saying you had to make them 100 million degrees Celsius, but then I said how fluorescent lights don't need that. So what's going on here? Well, what we're going to see is that, we need to define a few terms before we get there. So first things first, kinetic energy. This is the energy due to motion. So in physics class, we talk about kinetic energy quite a bit, and you can basically think of it like this. If energy is the money of the universe, kinetic energy is the money that you've got in your pocket right now. Right? So you can pull that money out, and you can immediately spend it on something. You can make something happen by spending that energy, by doing that motion. Potential energy is the money that you've got in the bank, right? So you'd have to go to the bank, you have to take the money out, and then you can use it. So potential energy is something that can be used later. It's yours, but you can't use it right now. Okay? So these 2 things are going to be really important. So the average kinetic energy, this is key, we use this to describe temperature. Oh, sorry, no. Average kinetic energy we use when we're talking about the kinetic energy of a substance, because it turns out that, in, say, for example, this glass of water, there is a lot of different particles in here, and each particle might have a different amount of energy because each one of them might have a different amount of money. But when we're talking about this particular jar, this beaker of water, we tend to talk about the amount of energy on average. So like, all of the big numbers, all the small numbers, what's the one in the middle? The reason we do that, of course, is just because we don't have the time to sit here and measure every single particle. We can't do it. Now, the average kinetic energy has a special name. It's temperature. That's what temperature is. Temperature is a measure of the average kinetic energy of the particles. Temperature is telling you how much money the average student has. So if I take the temperature of the room by sort of being like, okay, how much money you got, 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 and I go, okay, on average, everyone in the room has got about $20. $20 is a pretty decent amount of money. You can all get lunch. That sounds pretty solid. So right now we're at like room temperature money. If I do the same thing and I go around the room and I'm like, oh man, okay, so right now everyone's got at most $5. It's a little cold in here. We don't have a lot of money. We maybe don't be able to get much except maybe some coffee and a donut. So temperature, we're used to thinking of it as just how hot or cold things feel. But as we discussed when we talked about exothermic and endothermic, hot and cold and how hot and cold something feels is more of a discussion about if the energy is leaving you or going towards you. If the energy is leaving you, that means that you are becoming poorer in energy. You're losing your money. The world around you is taking it away. If the energy is coming into you, that means that you're gaining money. You're gaining energy. You're becoming richer. So if it's cold outside, which it's Winnipeg, it's always cold outside. If it's cold outside and we're sitting around outside, then we're going to be losing energy. We're going to lose money. We're going to slow down. We're going to get colder and closer, and we're going to get more and more solid until eventually we freeze into a block of ice. Conversely, if we're outside and the sun's out and the beach weather and it's really nice and warm, we're going to have the opposite problem. We're going to be getting paid too much energy. We're going to be getting energy so fast we're going to start to burn. So we want a nice even number. But that's what temperature is. Temperature is just a measure of energy, which is just the amount of motion that particles have. So what does this mean? Well, it means that it's possible for there to be no motion at all, zero motion. This is called absolute zero. It is when there is no kinetic energy at all. So if kinetic energy and temperature are related, then there is a temperature at which all particles of a substance will stop moving. We call this absolute zero, and it is at negative 273 degrees Celsius. Technically, it's negative 273.14, if I remember properly, but 273. So if I cool things down to negative 273 degrees Celsius, every single particle will be flat broke. Every single particle will not move. They will be completely and utterly still. Completely. The Kelvin scale there was just one that was developed by this chap called Kelvin. And the idea is that it's just sort of like talks about making an absolute value of zero being nothing happening. So it's a fairly simple conversion to turn one into the other. It's just subtract 273. The Celsius scale, they do the same thing. The Celsius scale just sets zero as freezing point of water because that's pretty useful for your average human. The Kelvin scale sets the 0 point as when everything stops moving because that can be useful for certain kinds of chemistry and physics. So here it is, right? It's the same basic scale. The size of each individual degree is the same size. We just put 0 in a different place. Now, 0 Kelvin to negative 273 Celsius, that seems pretty cold, and it is. Like, this is colder than space. Space, on average, right, if you take all of space, is about 3 Kelvin, right? So negative 271 Celsius. The coldest place ever is not actually space. Space is actually pretty warm. There's like stars and planets and stuff. I mean, pretty warm. It's still only negative 271. The coldest place that I ever have heard of is on Earth. Humans are pretty creative. Sometimes we've managed to find ways to make things really cold. I personally worked with stuff that got within 0.5 of Kelvin. So we were 0.5 away from absolute zero. And we weren't even working with anything that fancy. Now, why is that impressive? It's actually really hard to get to absolute zero, like as in impossible, technically. Because, well, take this cup of water here, right? If I tried to take all of the energy out of this cup of water, I'd have to put it somewhere, right? Because I can't destroy energy any more than I can destroy matter. You learned that in grade 10. So I'd have to suck all the energy out of this and put it somewhere else. But if I take all the energy out of the water, the cup still has energy. So I'd have to take all the energy out of the cup. But the air is touching the cup. So I'd have to take all the energy out of the air. So at this point, I've taken all the energy out of the air. I've now destroyed all life on Earth. And yet, that's just the air. The Earth has energy. And even space has some energy. There's a sun. You may have heard of it. It heats things up. Space is 3 Kelvin, not because it's not for lack of trying, but because it's almost impossible to completely isolate something from the rest of the universe in order to get to 0 Kelvin. So it's an idea, but it's not a reality. Now, this is a kinetic energy distribution curve. Oh, what are we looking at? It's a lot here. Okay. An analogy. Okay, we'll get to the picture. Analogy first. This is a whiteboard marker. Okay, it's an Expo dry erase low odor chisel tip blue. This I'm going to use to represent a particle. So this is a stack of 2 particles. Okay? So I'm going to put those right there. Here I have a stack of 5 black markers. I've also got a stack of 4 green markers and of 3 red markers. Now, what we see here is that I have a set number of particles. And what I'm showing you is that these particles exist in specific energies, right? These blue ones over here I'm going to say are kind of cold. And these red ones over here I'm going to say are kind of hot. And these ones in the middle are in the middle. So I've got here 1, 2, 3, 4, 5 black markers that have a particular energy. I'm just going to call those 2. And these markers over here are in 1, 2, 3, 4, and I'm going to say this is 3, and this one over here is 4, and of course this blue one then is going to be 1. So what this is doing is they're saying they're just piling up all of the particles of a particular type, and they're saying how many particles of each energy do I have? Okay, so now let's take a look again at the picture. In this picture here we see that we've got this curve that comes up and down. So down here in this low amounts of energy, I've got a lot of particles in this middle area, but not many on either side. And that makes sense. I've got a similar thing with this, right? So with my set of markers here, I've got this nice curve that goes up and down, and I see that this is the majority of the particles. Most of them are this energy level. Most of them are this temperature. But take a look what happens. As I heat up the particles, this thing gets lower, but also broader, right? I'm getting further and further to my right, where I have more and more energy. So what's going on here? Okay, well, that moment when you realize you did all this backwards. So we're going to want, there we go. That way it's the right way around for you guys. Okay, so what happens? Well, remember, particles are, by kinetic molecular theory, hard spheres. I've made them markers for this example. And they move randomly, and they collide, and they bounce. So when they bounce, right, a particle comes in, it hits one of the other particles, it gives it some energy. So if, for example, this black marker up here gets hit by another marker, another particle, and it gets some energy, it's going to have, let's say, more energy. So instead of being here, it's going to get warmer. So I could put it even here, like maybe it just goes from 2 to 3. But maybe it goes from 2 and it gets a lot of energy. Maybe this thing gets super hot. So it's going to go like way over there. Right? Just like we see in the graph. This particular graph goes way over here. Then another particle comes in and hits another one. Maybe it hits this one here. Right? And this one here is going to gain some energy now. Maybe it doesn't gain very much. Maybe it just goes there. And then another particle comes in. I'm going to hit this one here. And maybe it just puts it there. Right? It's random. We don't know where it's going to go. Each particle gets energy, and then each particle moves to just a random other place. So maybe these guys here, right, we'll say these two get hit, and one of them gets colder. That's possible, right? He gave more energy than he got, and maybe the other one also got really hot, so he goes over here. Maybe, you know, this guy here is going to bump and get a little bit more energy, and he's going to go here. Take a look at our curve now, right? It's broader. It doesn't go as tall anymore, but it goes from here all the way out to here. I used to have only 4 stacks of markers. Now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 stacks of markers. Now, most of the markers are still kind of in the middle, right? I got like a fairly large clump right here, especially if I move this guy over a bit to make it more symmetric. I've got this nice clump in the middle here, but again, it's random. Like I moved this guy just to make it look nicer, but again, he could have just lost a little energy and bumped down or stayed where he was. Or heck, maybe he'd go here, and this guy would go here. It's all random. But what do I see? I see that I have the same number of markers. I have the same number of particles, but those particles now have different amounts of energy. When the whole thing was colder, there was only a few options. I could only be in one of 4 places. So they were really stacked up high. But once I started to increase the total amount of energy, things got spread out more. And as things get spread out more, you end up with this sort of lower curve that's broader and not as tall. And it's all based on this idea that the particles are moving at random, right? Another particle comes in, hits this one here. Maybe it loses some energy and it comes over here, right? And then another one hits and it also loses some energy and it comes over here, right? Maybe it's getting cold outside and so it starts to lose energy. It starts to become colder and colder and colder. And as it's getting colder, there are less and less and less places where the markers can be. They start to stack up and you get this curve once again. And the reason why the curve looks like it does is because that's called a Gaussian distribution or a bell curve. It's a fancy way of saying that things tend to pile up with a lot of stuff in the middle and not a lot of stuff on the ends. So there we go. Things cooled down again. So we've got a taller but more narrow distribution of possible temperatures, of possible energies. Once again, it's random. So these two guys might get hit and then they bump up and they're way over here now. And this guy here, maybe he gets a little bit of energy. He goes there and this guy falls over. This guy on the top, maybe he gets a little bit of energy. Right? Maybe it's a really hot sunny day. So he's going to be there. And well, these two guys, they're going to get a little bit of energy and they're going to be over here somewhere. And heck, this red one, let's move that red one. Maybe it's going to go here. Right? And again, now there are lots of options, but they're much more spread out as a result. So these kind of curves, these kind of diagrams are just trying to show you how many particles there are at a particular energy. That's why it says percent molecules. In this case, I had an absolute number of markers, a specific number I was working with, but there's lots of molecules. And then what we see is that at a low temperature, we get a high graph and a narrow graph, just for the same reasons I've shown you. But as it gets warmer, the graph spreads out because there are more possible options, right? Simple. Like if I tell you that right now outside it's -40, you'll be like, what, really? Already? Oh, it's early. If I tell you outside it's -40 degrees Celsius, well, there's only so many options, right? -40 is the average. That's the middle. So that's like here. Well, only some of the particles are going to be colder than that, and only some of the particles are going to be hotter than that, but you're not going to find particles when it's -40 that are sitting at +40 way over here or something, right? The average particle is going to be pretty low in terms of its energy, so you're going to get them all stacking up on top of each other. Instead, I tell you it's like 20 degrees outside, right? Or make it 0, make this graph make sense. So it's 0 degrees outside. So maybe the middle here is 0. Well, you can have all those negative numbers, but you can also have all those positive numbers as well. So it spreads out more. So there's the idea behind these graphs. They're just trying to show you how many particles have what number of energy, what temperature. So right here, what we see, let's get our little diagram out of the way. Right here, what we see is that we've got 2 different temperatures, right? And the temperature of the second lower graph is bigger than the temperature of the taller graph, right? For the reasons that we just discussed. Okay, so here we go, and we have a series of graphs, different curves, right? This one here, it is at 100 Kelvin, but it's tall, and it's very narrow. That tells us this is going to be very cold. How cold? Well, let's turn it into Celsius, see if we can remember how this works. So the formula for this is going to be K is equal to degrees Celsius plus 273. So I'm at 100 Kelvin, so that's 100 equals degrees C plus 273. So what do? I take my 100 Kelvin and I'm going to subtract 273 from it. If I do that, I get -173. So this guy here is negative 173 degrees Celsius. That's pretty cold. Like, that's even colder than it gets here. Do the next one, 300. Okay, so I just put a 300 there. And I just take 273 from it. So I'm going to get, what, 27 or so? That should be about 27, I think, 27 degrees Celsius. Then we're going to do 600 minus 273. Let's get that out of there. 600 minus 273, let's see, we're going to get 327 degrees Celsius. I think that sounds about right, 327 degrees Celsius. And finally, we've got ourselves 1,000 Kelvin. Minus 273. 7, 2, and 7 degrees C. 727 degrees C. Let's see, did we get it right? Negative 173, 26, 327, and 727. All right. So, what are the things we're trying to see here? Two things. One, the kinetic molecular theory itself. The kinetic molecular theory describes how particles of a gas behave. It's the foundation of the idea of the particle theory of matter, right? That matter is made of individual particles. We ended up seeing that all of these particles, all of this idea sort of works in a certain way, right? We saw that every single type of matter ends up agreeing with the whole spheres with no volume thing, but that liquids are sticky and solids are both sticky and they don't move that much. But, as we just discovered, they still move because temperature is motion and all objects have some kind of motion, some kind of energy. And what we see is that, the Kelvin scale exists, that's going to be important, and we see about in terms of this distribution of energy, that we get lots and lots of energy possibilities when you're at high temperatures, so everything spreads out. But at low temperature, there's only a few options. So everything stacks up. Okay, that's it. It's a lot of things, and they're kind of a little disjointed, right? We talked about how solids don't move, but then actually they kind of do, but they only move in place. They fidget around like students who want to get out of here. We talked about how this distribution changes depending on the temperature. And that's where we're going to leave it for now. I'm going to stop it here. And next time, as we see here on this slide, we're going to be talking about intermolecular forces and the bonding between molecules. We've already covered this, but now we're going to cover it in more detail so we understand what it even means.